So a very good morning to you, okay? And today we'll be talking about the quasi-classical case. And I believe that we have already gone through perturbation theory, and we have gone through, we have not in general discussed variational principle, and we have discussed the domains of perturbation in time independent and time dependent. And now we'll be talking about the quasi-classical case. And I had already told you in my previous demonstration that you will consult Landau-Lipstick for quasi-classical case, because it's very beautifully demonstrated in Landau-Lipstick. Now, we would like to have an introduction of this quasi-classical case, and it has another name. You can also call it WKB, even though the W had independently proposed it, K had independently proposed it, and Brillouin had independently proposed it, and the three were amalgamated into a single theory, what is generally known as WKB approximation. So it is a quasi-classical study. So quasi gives you an idea that you're going to do something where you have the involvement of two things. And in physics, leaving string theory aside, we have two broad domains, the classical domain and the quantum mechanical domain. And quasi-classical works, it works between classical models and the quantum mechanical models. So, now, quasi, as it states, you can see, it means almost classical. Very, very close to the classical problem. You're solving basically your quantum mechanical problem in a framework of classical physics. But here, it's not pure classical in nature, right? There is some sort of inculcation in terms of the quantum mechanics. So it applies when quantum systems behave similar to the classical ones. Okay? So you exploit those regions, you exploit those states of the problems where your quantum system can be demonstrated in terms of the classical systems. And you think of quantum particles with some predictable motion. See, if I say pure quantum mechanical, what does that mean? It's pure probabilistic in nature. That's pure quantum mechanical. But here we are talking about the quasi-classical, right? That means you are thinking of the quantum particles with predictable motion. That means somehow you are managing to incorporate the trajectories of the particles, which is not the case when you talk about the pure quantum mechanical systems. So why we use, as we already know, as we talked about variational principle, we talked about perturbation, we try to solve the complicated problems which cannot be exactly solved. So WKB, which is also called as quasi-classical case, we can use this approximation to find exact quantum solutions, the solutions that are close to the exact solutions, because exact solutions are not possible, right? And it offers an approximation method. It's useful in tunneling. You understand that tunneling? When you have to explain the problem of alpha decay, how do you explain it? You explain it using quasi-classical case. You have quantum mechanical tunneling of the alpha particle, because it's not possible for alpha particle to break the the barrier width. The barrier width of the nucleus is approximately 24 to 27 megaelectron volts. And the alpha particle that comes out of these radioactive nucleuses, they have energies of the order of 4 to 6 megaelectron volts. You could not explain this using pure classical laws. You explain this thing using quasi-classical case. You explain this thing using something called as quantum mechanical tunneling. And you have the bound states, bound state problems, particle in a box, right? It's a bound state problem. You assume a particle in a potential where the potential is zero, but this particle is bound at the edges of that potential. The potential is infinite at the edges of that one-dimensional particle in a box. So it offers that approximation to the bound states and the quantization, which we obtain using Schrödinger's equation, and we obtain the quantized energy levels of the particle in a box. Getting my point? So WKB, it's very useful in understanding the tunneling, in understanding the bound states, and in understanding the energy quantization. And what is so important here is that you are giving some space to the classical ideas. You incorporate classical ideas. Now what is that? We'll see that. This is the core idea. The quasi-classical case, the core idea is that your wave function that you think about, it changes smoothly. It changes slowly. Particles move freely where energy is greater than that of the potential. E greater than V naught. E greater than V naught. This problem can be treated pure quantum mechanically, but this problem can be treated classically also. Getting my point? So I will call those problems, those regions, where you can solve a problem using classical principles. So I will say it's an allowed region for classical physics. And it is also allowed region for quantum physics. So you have you have a problem, you have a region where things are allowed for classical physics. They are equally allowed in quantum domain. And we can think about harmonic oscillator again. Okay, you have harmonic oscillator, and you can demonstrate harmonic oscillator using classical physics. So it's allowed. You can demonstrate a problem of harmonic oscillator in the context of classical physics, and you can also demonstrate it in the context of. So we call it classically allowed region. We call it quantum mechanically allowed region. But once you reach to the maxima of the harmonic oscillator, what will happen there? You have a harmonic oscillator, you have a pendulum, take a pendulum, okay? The pendulum has a limit where its kinetic energy becomes zero, right? From one side, and it becomes zero from the other side. This is classical pendulum, right? It has finite energies. But what about the quantum mechanical pendulum? Assuming that we have a quantum mechanical pendulum, a pendulum which is like oscillating electron, oscillating atom. For that, you don't have the classical limits. The energy of that particle can exist from minus infinity to plus infinity. Getting my point? But what we are trying here, we are trying to understand things in the context of classical and quantum regimes. So particles tunnel through barriers in the forbidden region. Okay? Classical physics has nothing to say about the tunneling at that point. We allow the wave-like allowed regions, and we allowed exponentially decreasing. We can see that if you take the example of harmonic oscillator, what is happening? to the forbidden areas. See, you have classical area, then you have something called a turning point. Then you have quantum mechanical area, right? So using quasi-classical case, you are trying to connect. You are also trying to connect the classically allowed regions, which are also quantum mechanically allowed regions, to classically forbidden regions. What we do there, we exploit the boundary conditions of the problem. But we know one thing. We know one thing, that for classical harmonic oscillator, you have a turning point. You have a point where the kinetic energy is zero. Right? You have a point where the kinetic energy is zero. Right? So you have to exploit the boundary conditions. Because you cannot say anything about those turning points. WKB is a pure failure for these turning points. So, very useful. As I said, we can understand the problem of alpha decay in nuclear physics using quasi-classical case. Quantum tunneling in your semiconductor devices. Okay? You have a quantum mechanical tunneling. Even in a p-n junction, you have a tunneling from one region to another region. And very useful in astrophysics and molecular models and behaviors in potential wells. It breaks down at turning points. As I said, think about the harmonic oscillator. Classically allowed region has a limit, but quantum mechanically there is no limit. Getting my point? But this WKB has nothing to say about your system at the turning points. Not accurate for rapidly changing potential. This is the most important argument of quasi-classical case. The argument is that your potential with respect to position, say if I assume a position of x, this potential should vary very slowly. It should vary very slowly. Only then you can think of using quasi-classical case. Otherwise, it will be a pure quantum mechanical case. It is still a powerful and suitable condition, even though it's a very starting of the advance of the quantum mechanics. The quasi-classical case that was used to understand some of the problems of physics. So, what this quasi-classical does, it tries to bridge the gap between quantum and classical mechanics, right? And it is conceptual and it's a very practical tool. You can demonstrate things and you can see them experimentally happening, and it approximates wave behavior. See, what is important here is that the particle that you have here, from de Broglie point of view, this particle has a dual nature. This is a quantum mechanical particle. It has a dual nature. So if it has a dual nature, it has momentum, yeah, and it has position. So there is inverse relation between the position and momentum, right? So if your momentum is large, the position is very probabilistic, right? If the momentum is less, then the position is close to the exactness. That means your nature is transforming from wave-like nature to the particle-like nature. Getting my point? So what is important here is that this quasi-classical case, it bridges the gap. As I said, it gives us approximate wave behavior effectively. So I think if you have any questions, you can ask me. So let's go with the theory itself and start learning it. So what we have a situation like this. If I think of a harmonic oscillator, This is my position, and this is my potential with respect to x. Now what is important is this v of x should be varying very slowly, right? And what we have let me call this minus alpha, let me call this plus alpha. Now, between minus alpha and plus alpha, you can treat this problem both quantum mechanically and classically. So I will call this region that you have, this is classically allowed region. Okay? Now at this point, what is happening to your classical problem? This is the extreme of that pendulum kind of example that I gave you. At this point, the classical physics fails. It doesn't tell you anything about this point. So these two edge points, they are called as turning points. They are called as turning points. So classically allowed region is from minus alpha to plus alpha. And after your turning points, the classical physics has nothing to say. So this region, either you call this region or you call this region, both of these regions are classically forbidden regions. So the problem is clear for us. We have a slowly varying potential, and what we assume, when this potential goes towards the turning points, before the turning point, this potential is assumed to change very, very slowly. It's a slowly varying potential. Right? And when it comes to the turning point, it has nothing to tell you about it. How the system is behaving. Right? And the same thing is true from both the directions. So what you have classically allowed region. But that doesn't mean that you cannot use the quantum mechanics to discuss that region. Okay? You discuss this region using quantum mechanics, right? And then you have the classically forbidden region. Clear? And you can even say this is a pure quantum mechanical region. What I'm telling you as the classically forbidden region. It's a pure quantum mechanical region for the harmonic oscillator. Is this clear? Okay. Now let's think about, we understand the basic equation to discuss the quasi-classical case, to discuss the quantum mechanics, is Schrödinger's time-independent wave equation. Okay? So I can write down the Schrödinger's equation, and I choose my problem as one-dimensional problem. I assume that the potential that's varying it's varying slowly. I choose that as v of x. So if I write Schrödinger's time-independent wave equation, what's that? That is d2 psi by dx2 plus 2m by h cross square e minus v of x, assuming that this potential is varying very slowly. Psi is equal to 0. Right? This is my Schrödinger's time-independent wave equation. And I can boil down this equation to d2 psi by dx2 plus k square psi equals to 0. Right? Fine? Now, I understand what this k is. Come on. this k square is, it is 2m by h cross times e minus v of x. No, this is not the scale, it is. Yeah? H bar scale, yes, it has to be h bar scale. Right? Can I write down this as h cross square k square equals 2m times e minus v of x? Okay, I can do this. Now tell me about, let's make it more formal. Tell me about de Broglie equation. What's the de Broglie equation? Lambda is h by p. And what is k? What we call as propagation vector. That's 2 pi by lambda. Right? This is k. How can I make it h cross? I will divide by 2 pi. I will multiply by 2 pi. So this lambda will be h cross 2 pi by p. Am I right? Something like this. So this is h cross and this is 2 pi. Now I can bring this, k is h cross 2 pi by p is correct, okay? What is 2 pi? If I bring lambda here, if I bring this 2 pi down, yeah, lambda by 2 pi will be k. Getting my point? What it will be? It will be k. So k will be h cross by p. So k will be h cross by, no, something wrong has happened. This is 1 by k. 1 by k is equal to h cross by p. So p is your h cross p. So we can see here, in the left hand side of this equation, we have the momentum, right? H cross k whole square, right? So this is momentum square is equal to 2m times e minus v of x. Is this right? Okay, now we have Schrödinger's equation and we want to write down its solution. And see what is important here in quasi-classical case. When we go with the solution of the Schrödinger's equation, we choose the solution in such a way that the exponential, the function is changing exponentially. And the amplitude of the function, do you remember amplitude? What is an amplitude? In terms of pendulum, amplitude. Okay? What should happen to the amplitude as it moves towards the turning points? Amplitude will increase, right? But what is the condition here? We want that the potential should vary very slowly. So what we do, we choose amplitudes in such a way that they change very slowly. So you choose two things. One is your exponential function. That exponential function means your function is changing very fast, which is basically the function of momentum. Because when you write down the solution to the Schrödinger's equation, you will have k. And you know k has a link with momentum. Getting my point? K has a link with momentum. So what does that mean? What does that mean? What am I trying to tell you? So I am making my momentum, I am making my exponential function to demonstrate the fast change. So exponential function is incorporating k, that means it's incorporating the momentum. And the constants that we introduce, a, b, they represent what? They represent amplitudes. Okay? You calculate them using normalization condition. So d values of amplitudes that we choose, we assume that they are varying very slowly. Now, I have Schrödinger's equation. What is that? That is d2 psi by dx2 plus k squared psi, the other function of one dimension x, is equal to 0. And I will write down its solution. Psi of x is a e to the power of, say I choose minus iota kx plus b e to the power of iota kx. Okay. I can also write down this as psi of x is a e to the power of minus iota alpha plus b e to the power of iota alpha. Right? And what is alpha? Alpha is kx. Alpha is? What is alpha? Alpha is kx. Come on. Alpha is kx. Right? What is h cross k? That is p. So what is k? That's p by h cross. Right? I can use that here. So alpha is p by h cross x. Come on, differentiate it. So what will be d alpha? That will be p dx by h cross. Can I do this? Yeah? Can I do this? Yeah? So I'll integrate. This differential and integral will go. So what will be your alpha? So what will be your alpha? Alpha will be integral p dx 1 by h bar. See what we're trying to decorate over Schrödinger's solution, right? And that's consistent with the quasi-classical case. So alpha is 1 by h bar integral p dx. This integral, we may have to use the boundary conditions when we have to deal with the actual problem. So what will be your psi of x looking like now? So psi of x will be a e to the power of minus iota by h bar integral p dx. Right? Plus b e to the power of iota by h bar integral p dx. You know, we will not choose this because this is exponentially raising very fast. Isn't it? So what we will be left with for the time being is this part. But we will go on here to boil down it to some more fundamental mathematics. Okay. Now psi of x. What is psi of x? It's a wave function. Right? It has everything to do with the position of the particle. It has everything to do with the position of the particle. Now, if you assume that pendulum kind of situation, you have quantum mechanical particle, suppose. The position is related with this particle, but we cannot measure exact position of this particle. That's why we have psi of x. And psi has no physical significance. What has physical significance? Probability density has the physical significance. So what does probability density tell us? It tells us the probability of finding the particle. Right? It tells us the probability of finding the particle. So if I think like this, psi of x whole square. Right? Somehow, if I think even from de Broglie point of view, this is probability of finding the particle. This must be inversely proportional to the momentum of the particle, as the problem states. As the problem states. The probability density, which is basically a function of the position, it has to have the inverse relation with the momentum. More momentum, less probability. More momentum means more motion, means more kinetic energy, less location. Are you getting my point? So you can think of inverse relation between the probability of finding the particle and the momentum of the particle, isn't it? More momentum, less probability to find it. And it has everything to do with my problem. So if I think of writing psi of x, it should be proportional to 1 by under root of p of x. Right? So I can incorporate this proportionality in my solution. I can incorporate this proportionality in my solution. What is that? That is psi of x is equal to 1 by under root of p of x, then e to the power of minus I alpha x, a is here, okay, you're right, plus b e to the power of I alpha x. Is it clear up to this? Now we can do simple mathematics here. Like what? You see this, okay, I can write down this is 1 by under root of p of x. This is a cosine of alpha x minus iota sine alpha x. Right? Clear? It's not clear. This is e to the power of exponent, e to the power of I theta. Okay, you're right. It has to be only alpha because we have incorporated x in alpha. You're right. It has to be without x. You're right. Thank you. Okay, this is fine. Then plus b cos alpha plus iota sine alpha. Right? Is it okay? Now, I would like to separate cos of alpha and sine of alpha. I can do that. So, what will be my psi of x? So, psi of x will be 1 by under root of p of x. And then you will have a plus b. A plus b cos of alpha. Then plus, you will have b minus a. You will multiply it with iota sine of alpha. Alright? And we generally solve these problems using some other constant. Say, if I take this a plus b equal to some zeta, this is cos alpha, and I want sine of something, okay? So this is zeta sine, say theta 1, right? And b minus a iota, I will equalize this with zeta. For this I need sine, for this I need cos theta 1. Okay, can I do this? I can do this. Okay, so what will be psi of x? Should I wait? So a plus b I chose equal to zeta sine theta 1, and b minus a times iota I chose as zeta cos theta 1, because this problem has everything to do with the phase. So that's what I'm trying to do here. I'm decorating my wave function. So what will be psi of x then? So psi of x will be, yeah, that will be 1 by under root of p of x. Then you will have zeta sine theta 1, then cos alpha plus zeta cos theta 1 sine alpha. Am I right? Fine. So psi of x can be thought of, zeta is out, under root of p of x is out, and this is your sine a cos b plus cos a sine b, that is sine of a plus p. So I will be using here sine of theta 1 plus alpha. Right? And I can choose my theta 1 plus alpha equal to theta. Can we do that? Yeah. Now theta is my phase. Okay? Theta 1 plus alpha is theta. So what will be my final equation for psi? So psi of x will be zeta by under root of p of x sine theta. So we'll stop here today, okay? And we'll proceed it tomorrow. So you can stop it. So very good morning to all of you. I welcome you all today. And we would like to continue our quasi-classical case. As I said, I have already developed some videos on quasi-classical case in which you can't see my face directly. So I will share those videos with you as well, so that you can do a comprehensive analysis of quasi-classical case. But here, let's get the gist of it, and this validity of WKB approximation, and let's talk about it. So again, I will try to remind you the basic assumptions of this quasi-classical case. I want you to concentrate again on these important basic assumptions, because you cannot develop a theory without having a clean understanding of the basic assumptions that are involved in developing a theory. So what happens here, what we have is the potential is varying slowly compared to the wavelength of the particle. So you see, wavelength has certainly the link with the position. It has a link with the distance. So what is happening is your potential should vary slowly compared to the wavelength of the particle. And the next important point is the wave function that we have. This wave function can be expressed in exponential form. We have done it yesterday. You might have seen that we wrote down the solution of Schrödinger's equation. In fact, we are dealing with a problem where you have two important regions. One is classically allowed region, another is classically forbidden region. And between classically allowed and classically forbidden region, there are two important points which we call as classical turning points. At the classical turning points, the physics has no explanation, right? But what we do, you will see through these videos that I may share with you, you will see that how we develop the connection relations from one region to another region. We call them ivory equations. You will check them on those videos. We develop those ivory equations, finding the solution of Schrödinger's equation in classically forbidden area, in classically allowed area, and then developing a connection relation between the two important regions. So the wave function can be expressed in exponential form, and you have classical turning points, and these turning points, because we We have no information about these turning points because classically the particle comes to rest. So we have to handle those points very carefully. You will check those things on those videos I'll be sharing with you, right? Okay. Okay, now let's get some mathematical way of describing that validity. What I was telling about, what you were looking at. So you will see that your wave function, it has an exponential relation. We have written down this, and we would like to generate this mathematical validity formulation for quasi-classical case. So you have these symbols, and this thing is something that we would like to discuss, that this d lambda by dx is very, very less than 1. This condition we will achieve when we will do a little bit of manipulations on the board. Is this clear? Okay. And one thing you have to keep in mind, see, this k, you remember k? What's this k? This k is under root of 2m by h cross square e minus v, right? This k has to be of two different k's. Why? Because in classically allowed region, e is greater than v of x. So you have k for that. And in classically forbidden region, v is greater than e. That means e is less than v of x. So there you will be dealing with a different k. But here I am trying to give the gist of the quasi-classical case. So I am taking my problem in a very, very straightforward fashion. So this condition, we would like to achieve this condition also. Okay, d lambda by dx should be very, very less than 1. Okay? Again, the same thing, slowly varying potential. dV by dx, it has to be very, very small than that of k of x and v of x. And once you move from classical turning points, you are in classically forbidden region, right? And energy not close to the potential extrema, no abrupt changes in the potential. These are the important conditions that you have to keep in mind while solving this problem, while trying to understand this problem, that the potential should vary very slowly with respect to the position, right? As I said, the WKB fails near the classical points. Classical turning points, because at the classical turning point, your E must be equal to V. So there is a failure of quasi-classical case to deal with these classical turning points. And what you have to do, you will see these things in those videos that I'll share, okay? You will see, you will understand how we develop these connection formulas so that you can connect classically allowed region with the classically forbidden region. And you can achieve some of the important results. Bohr's correspondence principle you can achieve from here. You can talk about the one rigid wall, the energy of a system in which one wall is rigid, or energy of the system in which two walls are absolutely rigid. So this is what I was trying to tell you. You will find those important things in those videos. So to conclude this introduction, it is a powerful technique. You can solve those problems which cannot be solved by perturbation, which cannot be solved by variational principle. And its validity hinges on smoothness of the potential. You cannot use this problem anywhere where the potential is very, very asymmetrical. Your potential has to vary symmetrically. And at the same time, it has to vary slowly with respect to the wavelength, with respect to the distance. It breaks down near turning points. This must be clear. There's no physics at the turning points. So widely used in physics, and that is what you understand. Now let me go with the flow that we have. Okay. I think we achieved yesterday something like this. Psi of x is zeta by under root of p of x, then sine of theta, where this theta is alpha plus theta 1. Right? You should keep one thing in mind, that this p of x has to be different in two different regions. And I would like to recommend that, because that you will check from those videos, I would like to recommend that thing. What is that? What we have, say for example, I will take K1, that's something like this, 2m by h cross square under root of e minus v of x. This is true for e greater